Well, hi everyone. It's a little bit different today. This is going to be a members only video for quite some time. Again, I appreciate everyone's support on the channel, but I wanted to show you what I do for a living. I test bridge foundations during construction, and we predominantly test either drill shafts or driven pile. We're here on a job today. It's a new toll project in Overland Park, Kansas. It's the US 69 bridge project. I'm working for the construction team of Ames Construction and Emery, Sapp and Sons. And today we're going to be testing a pile that supports this abutment on the north side of 119th Street. And eventually US 69 northbound will cross 119th Street here. So I'm going to show you how we prep the pile, how I put the gauges on, what I'm looking for. In post, I'll show you some data results that I'll drop in and maybe do a little bit of voiceover to walk you through what the results look like in a graphical format. But again, I hope this is of interest. Please let me know what you think in the comments, and let me know if you're interested in me doing similar deep dive videos on the specifics of bridge foundation testing. All right, so we're gonna lay out the center of our 4-hole pattern right here. All right, 30 inches to 8.5 feet, right? Mm-hmm. And then we gotta go 14 inches up from there for our hole, for our flange, or for our radios. Okay. Now go ahead and chuck up a bit. For the drill bits, you want to use 5/16 cobalt bit for a through hole on an H-pile. Get started, go ahead and drill your hole, your radio attachment. Okay, there you go. So you want to be perpendicular to the pile. You want to use a lot of downforce. I don't use cutting fluid anymore. As long as you use enough downforce, the tip of the bit will be cool enough without losing the temper. We're going to go the center line with this template. Why don't you just scuff a hole on these three? Just don't go through, just enough to scuff so you know where your location is. And you want to keep your hands clear of the edge of the template in case it spins. You don't want to jam your finger up against the flange. All right, so you got to know the total pile length. Subtract the distance to the gauges. So it's 27.75. There's the distance from the gauge to the tip of the pile. Hammer, we've already looked at D1942. Got our sensors. Okay, now we're going to start pairing everything up. All right, so right now it's Bluetooth, just pairing with the gauges. I can make sure everything's communication. I'm getting data on all 4 channels. It's 4-channel system, 2 strain gauges, 2 accelerometers. So one of the radios is spray painted pink. I'm designating that radio A. So we'll make a note which side of the pile that's on.
So what are you doing now?
We're securing the gauges to the pile. If that doesn't work, Kylan, just shove the pad in there. We'll have to try and tape these in somehow. They just gotta stay in there long enough to get the pile set. below the hammer. If it falls off with the first blow, we don't care. This Gorilla Tape doesn't seem that sticky. No. And you should spool probably. I think you're right. When you get the pile set in the hole and your helmet on your hammer set, I'll signal you like this when I'm ready to go. So I have to make sure the computer's still recording everything. So also, do you have somebody marking for set?
Yeah, I got my guys.
I think we ought to mark for set right out of the gate. Because I only think it's going to go, maybe you got a foot of slough in the hole. Past that, it's only going to go probably 2 more feet.
Bro, it's got to go 5'9" more. Minimum. What I was told a few minutes ago.
Well, I thought that was 5 to get the plan.
That's to get the plan, but then Donovan just told me inside the hole it's got to go another 5.71, so that's roughly 5'9".
All right, well.
If it don't go, it don't go. We're pouring concrete around them anyway, I believe.
Now, what we'll do is I'll watch the stresses. Even if I get capacity, if the stresses are okay, we'll try and get your 6 foot roughly.
Yeah, let me, I'll get one of my guys down here. I'm going to go ahead and hook him up, stand it up, and then I'll give you a couple feet of inch marks. Or you want to talk about just mark it off the
mark it off the blows.
Yeah, all right.
Mark it on the pile every 5 blows.
Yeah, right. I got it.
That way, if it takes up, we got a measurable. Okay, whenever they're lifting something, make sure you're watching. You never want to be underneath the boom or the crane, or close enough if something fell over it to get you. Hopefully he'll stick it where we can see the numbers. All right, let's go back to They pre-board 9 feet below the ground surface, 10 feet below the top of the template, which we're using for reference. So they pre-board into a weathered shale formation, Pennsylvania age formation, about 280 million years old. So typically, once you're into fresh shale, pile's only going to penetrate another foot or two. There might be a little bit of slough in the bottom of the hole, but it sounds like that's where the pile's at matches what they told me for pre-bore. So I expect that at most this pile's going to penetrate another 2 or 3 feet, probably less than 2 feet actually. So by the time we're done testing, the footmark should be close to 12 feet relative to the top of the template. Now, because this abutment is supported by MSE or mechanically stabilized earth wall, you need to have minimum pile embedment for lateral stability because you don't want a potential shear surface to undercut the bottom of the pilot. So they're looking for minimum embedment. If we need 416 kips capacity, that's 416,000 pounds or 208 tons. That's the required capacity. We may get that right out of the gate, but we'll watch the stresses. This is 50 KSI yield strength steel. So for pile driving, you're allowed 90% of yield strength. So we're going to limit our driving stresses to 45 kips per square inch, 45 KSI. So we'll just see if we can get that 5 foot of additional penetration for them. So we should end up around 15, 16 feet below grade to get their minimum, but we'll see. Okay, so the pile hammer we're using is an open-ended diesel hammer made by Delmag. The model's D1942. It has a maximum rated energy of around 43,000 foot kips. That's at the maximum stroke of around 12 feet. So it's an open-ended diesel engine in essence. So the top is open to the atmosphere. It takes about a 4 foot stroke before you'll see the top of the ram above the housing of the hammer. So if you see 2 feet of ram sticking above the hammer, that's a 6-foot stroke. Now the pile driving analyzer has a timer basically, and there's a formula you can use to calculate the stroke based on the time between blows. So the PDA will keep track of our stroke, but it's always good visually to match what you're seeing with what you're seeing on the computer. This is one of the predominantly used hammers in the Midwest, a D19 and a D30. That pretty much covers about 90% of the jobs. So the pile section is an HP 12 by 53. So the width of the pile is 12 inches. The 53 means it weighs 53 pounds per foot. So this is a common pile section used in the area. Typically, you'll see required capacities in the range of 400 to 500 kips for this section. Lately, I've been seeing a lot of screwed up plans for pile foundations. I've got a job coming up where they want 740 kips, which is way too much for a 12 by 53. So I'm seeing more of these kind of errors as we go forward here from consultant design projects that slip through the cracks with the DOTs. Now that job isn't here in Kansas. It's in a different state, Missouri. But so let's talk about this project. This is a US 69 project. Originally, it was built in 1969. That's not why they named it that way, but US 69. And this area of Kansas, Overland Park area, which is greater Kansas City areas, had tremendous growth. So there's a project, about a $600 million project to add a single toll lane in each direction, so northbound and southbound. So I'm really looking forward to that. This is going to be about a 4-year project in total. It's going to extend from 119th Street here down to 167th Street in Overland Park. So right now they're lifting up the pile hammer, the D1942. They're going to move it in place and set it on the top of the pile. There's a helmet that goes over the top of the pile. That's the drive helmet. And I'll double check my computer. Everything's recording. I'll signal them to start driving. I'm going to have them mark the pile penetration for every 5 blows right out of the gate since we're in a pre-bored hole. I've taken the precaution of lowering the fuel setting on the hammer to 2 out of 4 max because I don't want to overstress the pile. If we get plenty of movement, or let's say the movement's not enough, very low movement, say a half an inch at 5 blows, and the stresses are okay, then I'll have them increase the fuel setting from 2 to 3. We'll see how it goes. So these hammers have 4 fuel settings. Some call them 0 to 3, others call them 1 to 4. The lowest setting's off. 4 is the maximum fuel setting. So it controls how much fuel, diesel fuel, comes in from the injectors into the combustion chamber. And it's a bounce chamber, so they'll pick up the ram with a line and then let it free fall. That'll compress the fuel-air mixture as it compresses and will detonate, which will throw the ram up in the air. Of course, the detonation imparts a downward force on the pile. That's the force that's driving the pile. So if we're close to getting to our required depth and we think we've got required capacity, you don't want a pile set more than about 2.5 inches and 5 blows because then you'll overpredict the pile capacity with the PDA. And if you're much under, say, 1 inch and 5 blows, you're going to underpredict. So, if we're going to underpredict, I'll try and run the PDA to an extra capacity so I know I'm good. So we can always adjust the fuel setting, but let's say I can't do it anymore. We'll typically shut off the driving when they're a 1/2 inch at 5 blows. I've probably tested over 1,400 pile for bridges, and I've tested probably 12,000 drill shafts for bridges over the last 23 years. So one of the things you want to watch for when they're setting the hammer is that they don't bang into my gauges. These gauges cost about $4,000 on each side of the pile. So there's about $8,000 worth of gauges sitting on the pile right now. So I've got one of my sons going to get his safety harness because when we're done driving, there's no way this pile's going to go more than a few feet. So our gauges will be several feet above the ground. So he'll have to run the man lift up there to get it. Now, in cases where I'm totally confident where the pile's going to take up, like this one, You know, it's got another 6 feet to go to get to plan tip elevation. I don't think we're going to get there. So I would have been tempted to put my holes right about the spot above the ground where I thought the pile was going to stop. But because this schedule is so critical on this job, I can't risk holding the crew up for even 20 minutes. If I was wrong, I would have drilled the holes in 2 locations at the top and where I thought the pile was going to take up. And if for whatever reason the pile went longer than that, we'd have to stop. I'd have to take gauges off and put them back on the top of the pile. So we just put them on the top of the pile. We got plenty of room now. But again, I don't think the 16-foot mark's going to go below the template at all here. So in my opinion, anybody involved with pile design and installation needs to have experience on actual jobs watching how pile are installed. Now, like I said, I've tested a few thousand driven pile, and we see day in and day out how deep the pile goes in the certain formations or soil, and what kind of capacity you get for given depths or soil conditions. And you internalize that, and you have a much better feel for what's going to go on. In fact, I've brought in brand new people with no background in the industry, and inside of 3 months, they may look at a set of plans and say, there's no way we're going to get this far into the bedrock to this minimum tip. And I'm like, you're exactly right. But yet it went through the designer who set those depths. It went through the DOT who approved the plans. So we're seeing more and more of this where there's a disconnect between the design intentions and what actually happens during construction. This job's gone pretty well. In general, though, I think they were, as a schedule, they estimated a little long on the pile lengths just to be on the safe side. It's easier to cut off excess piling than it is to splice later. And let's say you splice a short section, that weld may be in an unfavorable location or an exclusion zone. In Kansas, typically they don't want the weld within 10 feet of the web wall that contains all the piling. So they got foot marks on the pile. Some of them got wiped off, so I'm going to have them put additional foot marks there. The lowest dot is 10 feet. So obviously they don't have enough boom on this crane to set the pile hammer over the top. So they're going to have to remove this chain, spin the leads so the open side of the leads go over the piling, and then they'll set the hammer on top of the pile. So when you're driving a pile, roughly there's a blow every second, depending on what the stroke is. So typically for our region, you're driving a pile less than, say, 10 or 15 minutes. Sometimes it could be longer if you're in deep soil formations and it's a friction pile. But in this case, we'll have a few minutes of driving and we'll be done. So to start pile driving, the crane operator will have a winch that he'll pull the ram up with a cable, and then it trips and automatically releases when it gets to the top position. So when we're driving, since we're already pre-bored into bedrock, I'm gonna have him mark the set every 5 blows. So we actually got capacity about 3 feet in to where it's where I thought it would take up, but they were trying to get as close as possible to their planned depth to get good embedment or foundation below the MSE wall. And so we didn't quite make it to 16. We ended up about 14 and a half feet, but I think they're going to call it good. All right, so my son, Hyland, one of my 3 boys, he just got the gauges off the top of the pile. I knew that the top of the pile was getting a little mangled. I could see the stresses. The max stresses exceeded about 52 KSI, but the average was just below our threshold at 45. Bottom stresses were around 30 KSI. So I knew we could go a little while because they wanted to get that minimum penetration, but eventually I had to stop because they're going to mangle up the pile too much. They've got about 5 feet of pile they can cut off to be above cutoff elevation anyway. So we're good here. So it's all wrapped up. Well, I hope everyone enjoyed that session today of what it takes to drive a pile and to monitor its capacity. You know, pile driving is a live test. So the data you collect, it exists in a moment in time and can't readily be replicated. You can do restrikes, but in cases where you're driving to bedrock, you don't want to continue driving because you run the risk of damaging the pile. So it's very important to have your testing firm who has a lot of experience and is able to get good quality data and know big picture what it is they're trying to accomplish here, not only in terms of capacity, but minimum embedment depths and other considerations.
So I've taken the data off my field computer, put it on my analysis computer, and this is a graphical representation of our pile driving test data. In the left-hand panel is capacity and average stress versus elevation. The middle plot is average bottom stress and energy transfer ratio of the hammer. And then we have hammer energy that's delivered to the pile, as well as the hammer stroke. So as you might expect, anything over about 200 kips capacity for this soil profile indicates that we're already into the bedrock, which we already knew from the pre-bore depth. And then the capacity increases with depth. Sometimes you can break through into more weathered zones, but then finally we get into pretty fresh shale and the capacity increases with increased driving depths. And again, we want to limit our stresses here, so we're good on all counts. Then we use another program to perform what's called signal matching analysis. And what you do is you idealize the pile soil system as a series of spring and dash pots. And you iteratively assign different properties to discrete portions along the length of the pile, adjust those parameters until you get a calculated curve that matches the measured curve. Capacity falls out of that. So in this case, we had a total capacity of 458 kips. 235 kips was from side friction, and 222 kips was from end bearing at the tip of the pile bearing into bedrock.
So thanks for watching, everyone.